Hey guys, well it's time for a bit of chemistry, organic chemistry to be precise. This is the first in a series of 3 videos on organic. We're going to have a look at how the whole family fits together, the homologous series and functional groups and things like that, isomers, and then we're also going to have a look at naming. So let's first of all get our head around organic chemistry. What's it all about and how does it all hang together? Well, it's actually quite similar to getting to know a very large family. Now, I don't know how big your family is, but I wouldn't be surprised if you've got some cousins and aunties and uncles, maybe even nephews and nieces and grandparents, and then you've got those second cousins removed, and then you've got those guys who live in Tanzania that you've never actually met, but you've got the odd postcard, you know, that kind of thing. So imagine they all get together at a big family wedding, and you've got the job of getting to know them. Now that is like getting to know organic chemistry. So let's have a look and see how the whole thing fits together. Organic, the organic family. Now, the first level, the first layer of learning is really recognizing the homologous series and the functional groups and how those all fit together. So in the big extended family, there's a whole bunch of nuclear families. So in organic, what we're talking about there is the alkanes and the alkenes and the blah 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 and the so on. Those are all the little nuclear families within the larger extended family. Okay, and you know that they're a family because they all share something in common. So that family that came from Tanzania, well, he actually married into a Maasai tribe, and like this, they're all like super tall basketball player kind of people. So you can see them from across the room. That is an identifying factor. And that's exactly what a functional group is. It's something that is distinct and unique to that group of chemicals. So alkanes, for instance, they all are joined by single carbon-carbon bonds throughout. Okay? Alkenes, well, there's going to be a double bond somewhere in the mix. Alcohols and OH, etc. Those are the identifying things. That is the functional group that identifies the homologous series. So whether it's blonde hair, very tall, eats like a horse, has a very big nose, whatever that distinctive feature is, that is the functional group. And you've got to get to know your way around who's who and start putting people into their family, start putting the different chemicals into their different families. So that's level number 1 of learning. Level number 2 is where you now need to start to get to know some names. Now, if you're like me, sometimes that can be a bit of a challenge. But we fortunately have a very helpful tool when it comes to organic chemistry, and that is the IUPAC system, International Union of Pure and Applied Chemists, for those of you who are wondering. So it's men and women who wear white laboratory coats, and they wear those awesome spectacles, and they walk around all day just thinking of rules to making chemistry. Fantastic. It's like the United Nations of chemistry, basically. So these guys came up with a fantastic naming structure for organic, where they look at every single little detail, and they number it, and they dash it, and they put prefixes and suffixes and everything like that, and you come up with this awesome long name that is enough to choke a donkey. And basically, that gives you an exact recipe for what that substance is going to look like. So rather than on the back of the sort of pharmaceutical drug, you know, the chemist having to draw out exactly what methylbutanoate looks like, you can just put methylbutanoate. And if there's 1s and 2s and so on, that all fits in with the name. So that's the objective of it. It's quite complex. We're going to go through some of it just now. But once you've got it, it's a doddle. Okay, so just getting to know the rules, that's all. Then the third level of learning is getting to know the physical properties of organic compounds. So for each of these families, there's a whole bunch of history. There's some facts and figures. So let's say Aunt Zelda, she was born in Durban, and as a result, she loves bunny chow, that kind of thing. Whereas Uncle Bob was born in Bloemfontein, and he only eats boerewors, that kind of thing. So it's just some physical facts and figures about the family. That was very good alliteration, wasn't it? These, again, is just a lot of learning But there is one thing that ties all those together, and I'll save that for when I get to that section. But there's a bit of physical properties. There's things like their boiling points and their melting points and whether they dissolve in each other's in compounds and things like that. So that is the third section that we're going to have a look at. And then the fourth level of learning, just making a bit of space for myself up there, is then the chemical properties or the reactions. Okay. And this is now where things start to get interesting, because you mix this with that and it actually makes this. Or it reacts with something else to make that, and then you get this. And if you mix that with that and you add a bit of hydrogen, then you're going to get this, etc., etc. And the whole thing becomes an interweaving web of interesting relationships. It's a bit like Issy Dingo or Bold and Beautiful or something like that. It's a real soap opera of relationships. There's nothing predictable at all. You just have to get to know how people operated. And you'll know not to put Aunt Zelda and Uncle Bob next to each other at the table, because then they'll fight about bunny chows and boerewors and things like that. So basically, that's the big picture of how organic all fits together. Get to know the names, get to know the homologous series and the functional groups, the individual families. Then get to know how to name them all. Get to know their intermolecular properties that determine their physical properties. Bit of a hint there. And the chemical properties. So this is what we're going to tackle in this video, and I'll do those two in a little bit later. Alrighty then. So let's just have a quick run through the homologous series. I'm not going to draw them up all up on the board. You've got a table in your notes, and you've probably got one from school as well that you can have a look at to get to know those very well. It's just a bit of memorizing, but just to help you in the journey, the best way to do it is to group them together. So the first batch are the hydrocarbons, named as such because that's all they contain, hydrogen and carbon. Okay, so those are your alkanes, alkenes, and alkynes. And a nice way to remember which is single, double, and triple is that it is alphabetical. Okay, so alkanes, alkenes, and alkynes. 1, 2, 3. Single, double, triple bonds. All right. Then the next little pair that you could maybe think of is when we take usually an alkane, could be an alkene, maybe even be an alkyne, and we take off one of the hydrogens and plonk something else on. So there's the haloalkanes, which has a halogen, okay, not Adele sitting in the inner limit. So a halogen where you've got a fluorine, chlorine, bromine, iodine sticking somewhere on an alkane to make a bromobutane or something along those lines. Or we could also put an OH, which would make it into an alcohol. Okay, so those two you can get to know quite well. Then there's another little pair, and they share the same functional group. So it could be misinterpreted, but it's where the functional group falls on the chain that determines what it is. That's the functional group. It's called the carbonyl group. And if it ends up on the end of the molecule, in other words, this just has an H on it, and then whatever it has going on there, then it's an aldehyde. Aldehyde on the side is the little rhyme to help you remember that. But if it appears in the middle, in other words, it's going to have a carbon on either side of it, then it's going to be a ketone. All right. So that little pair go together. We'll talk about isomers and everything just now. I'll leave that there. Then there's another pair which also share a functional group. It also has a carbonyl part to it, but then it also has a hydroxide. So you've got carbonyl, you've got hydroxide. Sorry, carbonyl, hydroxyl, not hydroxide. Hydroxide is the inorganic way we talk about it. Hydroxyl is the organic way of talking about it. Hydroxyl, carbonyl, hydroxyl, and we end up with carboxyl. I'm not making it up, I'm serious, that's what it's called. Okay, it's a carboxyl group. So that you'll find on the end of a carboxylic acid, okay, as well as in the middle of an ester. So as it is, that'll be vinegar with another CH3 added on to the end of it. But take off the H and put another C, blah, 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 with a little methyl or something on the end there, suddenly it becomes an ester. Now, I'm not going to go through all the distinctives of each of those particular families. That's something for you to research and get to know, and being able to identify who's who and what's what. Right, so that's homologous series and functional groups. Let's have a quick look at isomerism and how that whole thing works. Once we hear, these guys are prone to making isomers because they're so similar. They share very similar looking things. Let's look at an example with this carbonyl group guy. So, for instance, ladies, what do you take your nail polish off with? Nail polish remover. Well done. Which is acetone, okay? Which looks like that. It is the smallest ketone that we can actually get, because you're going to have a carbonyl in the middle. It's got to be in between two others. That is acetone. All right, that's what it looks like. Propanone is the normal name that we'd give it with IUPAC naming. We can make an isomer of that. Now, what is an isomer? Just to clarify that, an isomer is isomers are two substances that have exactly the same molecular formula. In other words, the same ingredients, the same molecules make it up, but a different structural formula. So if we were to write the molecular formula of that, it's C3, 3 C's, H6O. All right? Now there's another way of putting that together. It's kind of like, I don't know if you guys ever played with Lego. I was a Lego fanatic. It was like insane. I was obsessed with it for like 3 years of my childhood. Anyway, you get your Lego little thingy, and you can make the actual contraption, whatever it might be, a spaceship or a truck or something like that. Then on the back of the box, you're going to have all sorts of different iterations of how you can put those pieces together. And that's kind of like what we do with isomers. So take those ingredients, break them apart, and then stick them together back again in an appropriate way. Obviously, you can't just put them higgledy-piggledy, because we know that carbons have to have 4 bonds, hydrogens are only going to make 1 bond, oxygens are going to make 2 bonds, and things like that. So there is a specific method. Don't make weird, funky things like that. So what we can do is, instead of having the functional group right bang in the middle, we'll pop it in the end, thereby making a different substance. And there's all the H's. So if you have a look at the molecular formula of that, we've still got 3 C's, we've still got 6 H's, and our O. Same molecular formula, different structural formula. So that's an example of an isomer. What type of isomer? Well, what's different about these is the fact that it's a different functional group. Okay? You might say, well, they're both carbonyl. Yes, they are, but they're different homologous series. This is a ketone, propanone. This is an aldehyde, propanal. So that is an example of a functional isomer. Okay? The 2 other types of isomer that we can get are positional and chain. So the positional one's really easy. Let's take 2-bromobutane for a nice little simple example. So 2-bromobutane, but 4, bromo on 2, and the rest are hydrogens. I hope you guys have all got the hang of something like that. What is an isomer of 2-bromobutane? Well, positional isomer, easy as pie. You just say, well, let's take it off 2 and let's put it somewhere else. So could I put it here, for instance? Let's just move it across to 3. Well, no, that's not an isomer, because actually if you start counting from the other end, that's 1, that's 2. It's still 2-bromobutane, so you haven't made anything new yet, okay? But what we could do is take it off the middle ones altogether and pop it over there, and then that becomes 1-bromobutane, which is an isomer, it's a positional isomer. There is another way of making an isomer with this thing here. I'll just keep the bromo as part of the whole mix for now. And this is to make a chain isomer. Now, you can't just bend the end. So let's take that off, put an H there, and let's say, well, what about that then? Okay, there we go, there's something different. No, that is not different at all, because we've still got 4 in a row. It's still exactly the same as what we had previously. So that's no good. That's not an isomer. Put it back there. What we have to do is a sneaky little trick, and you actually have to, you can't just bend it, you have to break it, all right? So if you can just imagine what we're doing, Lego contraptions, you have to kind of snap the end off and stick it on in the middle, all right? So what we'd end up with is 3 C's, and then that thing you would end up coming on here. Okay, leave Br where it is, and the rest are all hydrogens. So that's an example of what we'd call a chain isomer. And as I said, best thing to do is to snap the end off and plonk it somewhere in the middle. Once again, same molecular formula, C4, H9, Br, for both of them, but a different structural formula. So that's isomers. And then the last thing to have a look at is a bit of naming and how to draw correctly to get all the marks, your structural formula. So naming, there's a bunch of rules. I'm not going to go through all of them. You guys are going to have to do that on your own, but I'm just going to go through a nice juicy example so that you can see some of the quirky things that you have to watch out for. So here we go. Something like that. Double bond in there. There's a bromine in there. Put a methyl group on there. And another methyl group over here. And let's put an ethyl group over here. And then we've got some H's. I'm going to put a chlorine over there for fun. Okay. And before we get too carried away, let me just put in some normal H's. Good. All right. Whew. Okay, let's name that one. So where do we begin? Let's identify the homologous series first of all. All right, so the dominating thing is the fact that we've got a double bond there. So we know that the very, very, very last thing in this whole, the surname of this long name that we're going to put together is going to be an ene. All right, it's an alkene. So we're expecting an ene. So that's going to come somewhere over here. It's often helpful, by the way, to sort of put the pieces together and then construct your name. So I'm going to do that in kind of rough. In this section, you can do it in pencil or on rough paper, but then we're going to bring all the pieces together and compose our whole massive name. So it's going to end with an ene. Let's then identify the longest chain that we've got. Okay, so we've got 1, 2, 3, 4, 5, 6, 7. The main chain that I've drawn. However, I hope you've noticed that my chain actually does bend off to the left. 1, 2, 3, 4, 5, 6, 7, 8. And that is longer than the 7. So it's going to be an octene. All right, nice long name. So that's going to be our prefix of octene. There's no dash, I'm just composing. Then let's start to have a look at some of our side chains. We've got a bromo, and we've got chloro, and we've got a few methyls hovering around the place. Now, on numbering, generally we number from the side so as to keep the overall set of numbers as small as possible. So without that double bond there, I would have to have a look and see, well, how many methyls have I got, how many chloros and bromos, and which side keeps the overall pack of numbers the smallest. It's quite a mission with such a huge bunch of side chains like I've got in this case. I suspect I would actually start numbering from this side, but I could be wrong. But I don't even have to worry about deciding that because of the fact that I've got a double bond. And as soon as you have a strong functional group like that, or an alcohol, or a COOH, that then becomes your primary thing. You treat it like a diplomat, very important person. You number that one first and you keep that number as low as possible. So I'm definitely not going to start numbering from here. I'm going to start numbering from this side. So that's going to be my first carbon, that's going to be my second, and so on. I'm just going to put them in. You can do this in pencil, and it does help to make sure that you get your numbers all correct. Once you get the hang of it, you may not need to do it, but it's a good starting place. So in fact, it's going to be oct2ene or 2-octene. I'm going to squeeze it in the middle there for now. And then let's get going with some of the other things. So let's work with our bromo first. That's going to be a 2-bromo. And then our chloro is going to be a 6-chloro. And then our methyls, we've got 1 on 3. We've got 1 on 5. and we've got 1 on 6. Okay, so we've got a 3, 5, 6 methyl. But before we jump into putting the methyl, we have to say that there's 3 of them, just to remind ourselves, and we would go for trimethyl. Okay, so that's the sort of name that we've got to put together. Now that we've got all the ingredients, let's compose the whole thing together. And what we do is we put the prefixes in alphabetical order. So bromo, chloro, and then methyl. Don't worry about the tris and the dis. That's not relevant. It's the M that we'd be interested in. So here we go. The whole name would be 2-bromo, 6-chloro, and take note of the punctuations. It's dashes between letters and numbers, commas between numbers, and when it's letter to letter, you just let it flow. There's no gaps, there's nothing. 3, 5, 6 trimethyl oct 2 ene. I hope we've got that right. Okay, so that is a monstrous name. 2-bromo, 6-chloro, 3, 5, 6 trimethyl oct 2 ene. Whew. Okay, you're not going to get something as complicated that as in your exam. You'll be glad to hear. So if you can nail that, then you can do anything. And the last thing let's do is let's go the other way. Let's give you a name, and this time I'm just going to take a nice simple one from a matric exam paper, and let's put it into a structural formula. So, I can't remember which paper this was from, but ethyl butanoate is the kind of name that they're going to give you and say, draw the full structural formula for that compound. So I'm just going to write the name so that you can sort of see it and think it through. If you want, pause the video and try and draw it yourself before I do. Okay, ethyl butanoate. What kind of compound is it? Ester. It's an ester. Okay, nice smelling one. Might smell like a bit like pineapple or apple or something along those lines. Ethyl, that gives us an indication that it's going to be a 2. Okay, so we start with that. CC, Signor. And then butanoate, that is going to be joined by the O of the functional group to the C double bond O, and then the rest of the C's follow. We've already got 1, so it's 1, 2, 3, 4, and you can then fill in the H's. Okay. So when naming esters, when drawing esters, the O separates the two halves, so it's like a double barrel name. The O, the other O, is part of the O8, okay? And that actually came from, if you're thinking of where this reaction came from, by the way, that came from the butanoic acid. So the butanoic acid would have become butanoate. This would have come from ethanol. The ol becomes the il, the oic acid becomes the O8. And then just deconstructing it, we can have a look, and if we were given the compound and trying to name it, split it at the O, look which side has the other O, and that's the but, so it's the butanoate, and there's the ethyl. I hope that makes some sense. Okay, cool. That's part 1. Do a bit of practice on that. You got some past paper questions. Enjoy. We'll catch up later. Ciao.